All right, today we are going to derive the expression for an electric field due to a thin, straight, isolating or insulating wire of length L at point P, which is equidistant from each end. So here in red we have our insulating wire. It is straight, insulating wire again, so the charge doesn't move within it. Okay. Has a length L, and we're going to determine the electric field at this point P over here, who is equidistant from each end of the wire. So first thing we're going to do is we are going to consider the electric field from one small little section, and this is a recurring theme for us when we do these derivations. We always consider the electric field at a point, and then we end up integrating. So I'm going to call this little point right here at the very end, I'm going to call him point I. So then he will have an electric field exerted on this point right here. And it would be along this line like this. I will say that this point is distance D away from the wire, perpendicular. Okay, if we drew a line perpendicular from the wire to the point, it would be a distance D. We will consider this to be the y-axis. I'm going to go ahead and put some numbers in here. So if the entire length of the wire is L, if I consider this to be the origin right here, then this would be location L over 2, and this one down here would be negative L over 2. Now this is going to be important when we decide we're going to integrate, because remember, we're going to determine the electric field at this little point right here, infinitely small little amount of charge, but then we're going to integrate it or sum up an infinite number of these little lengths from L over 2 to negative L over 2. Okay, so we'll be summing everything up along here. So, if we consider the electric field caused by this little piece I, it would be directed this direction. But I'm hoping that we can have a symmetry argument that the component that is in the y, in the negative y, caused by this guy all the way at the end, well, he would be canceled out by a component from this little guy on the other end. So in the y, we have this situation where the electric fields cancel. So all we really need to do is sum up the electric field components in the x direction. So we're looking for this little component right here for this guy. Well, if I call this angle theta I, theta sub I, because if you notice as we sum these up, this angle will in fact change. Okay, so this is the angle only for part I. So this angle over here is also theta I. So we are really interested in the component right here, which is cosine. So if this was the electric field from part I, we are interested in this component over here, which is cosine. So this would be EI cosine theta I. So we'll come over here and we will start this. So we'll go back to black. So the electric field for piece I, again, piece I is that tiny little piece on the top, in the x, that is equal to his total electric field, but we're interested in cosine theta I, okay, only the component in the x. So then this would be equal to 1 over 4 pi epsilon naught, Coulomb's constant, All right, so now it's times the charge over how far away it is squared. Now we need to be careful here. Um, the charge is just some tiny little piece of charge here, okay? The charge is equally distributed along the length of this. So this is where we put in our linear charge density, lambda, equals the total charge over the total length. Therefore, if we are considering a tiny little change in charge, we'll have a tiny little length. So I'll call it little l. Okay, so now you know what? And so instead of calling it a little l, this is in the y, so it'll be a small little change in y. We will call it dy. So let's change that up. Okay, so now I can see that dq equals dy lambda. So we can use that. So now, Coulomb's constant times the charge. The charge on that little thing is just dq, the tiny little charge. And that is over how far away he is squared. So I will call this distance away r sub I. Again, the distance away for each one of these changes. So this is not a constant number. The angle is not constant. And also the distance away is not constant. They both change. All right, so then this is r I squared. So this is Coulomb's, or this is the electric field at this point caused by this little piece up here. But remember, we are only interested in the component in the x. So that is times cosine theta sub I. So now, there's a couple things that we're going to have to do, a couple different things that we could substitute in. So if we go back to how far away this is, so this distance, r sub I, well, that is actually equal to, think of the Pythagorean theorem here. This is equal to the square root of the y coordinate at that point squared plus d squared. D squared does not change, y does. So now, a couple different substitutions that we can make. R sub I, the distance away for the charges, is the square root y sub I squared plus d squared over here. But again, looking over here, so that will get me y's instead of an r here. I want to get y's everywhere because I'm summing up everything along the y. So the r sub I is cool. I can do a substitution. Now I need to take care of this cosine theta. Well, looking over here at my picture, cosine theta, well, that equals, thinking SOHCAHTOA, that is the adjacent side, which is d, over the hypotenuse, which is r sub I. So it's d over r sub I. Again, that's using SOHCAHTOA. But r sub I can write with y in it. So this cosine theta is actually d over the square root of r, or y sub I squared plus d squared. And then finally, this charge, this tiny little charge q, looking at my linear charge density, this tiny little charge q would actually be lambda times dy. So the tiny amount of charge on that tiny little wire would equal lambda times dy. So now that I have all that, I can go ahead and use substitutions in here. So now the electric field from that tiny little piece I in the x, all right, it is right here, 1 over 4 pi epsilon naught times tiny little charge q, which is lambda dy, over r sub I squared, but r sub I is the square root of y sub I squared plus d squared. Well, I'm squaring it, so when you square the square root, you're just left with y squared plus d squared. Okay? And then finally, that is times cosine theta, and cosine theta is d over the square root y sub I squared plus d squared. So, make sure you know where all this came from. This guy is this guy right here. This factor is this one. And finally, this guy right here was cosine. All right, so now we can clean this up just a wee bit. So I do need to be careful. So this is a dy. So notice now I have a function with only y's and a constant d in it. That's all, the only variable, the only thing changing in this whole thing of all these symbols and letters is y. And that's also my variable of integration will be y's. So I have this lambda in this d up top, but I have to be careful how I write that. I don't want to write the d first because then it will look like the differential of lambda when it's not. This is lambda. D is the distance away. So I will write this as 1 over 4 pi epsilon naught, Coulomb's constant, times lambda times d, and then that's times the differential of y, that tiny little change in y. And then that is all over. On the bottom here, I have two like bases being multiplied. This is to the 1/2 power. This is to the 1 power. So this is y sub I squared plus d squared to the 3/2 power. So now I have the electric field from that little piece in the x equals this expression. So what I want to do now is add up all of the little pieces from here all the way down to here. So when you integrate both sides of the equal sign, you would then have the total electric field in the x equals, okay, the integral. Now I can pull out a whole bunch of constants. Lambda's a constant, d's a constant, 4 pi epsilon naught, those are all constants. So this would be lambda times d over 4 pi epsilon naught times the integral, and we're summing up from L over 2 to negative L over 2 of dy over this. Now, trying to figure out the integral of this would be very, very, very difficult. For this derivation, it is okay, and you are expected to have memorized an integral. So I will give that to you now. I'll put it in red so that you recognize that you need to memorize this. Here's a little star, and this is the integral. Anytime you have an integral with respect to a variable, and you have a constant squared plus that variable squared raised to the negative 3/2 power, just like this, well then the integral is the variable of integration on top, the constant squared times the square root of a squared plus x squared. Now there would be a plus c, but we are dealing with a definite integral, so you'd be adding the c and then subtracting the c, so it would just be gone. So utilizing this now, we have lambda times d 4 pi epsilon naught. This would be y over d squared times the square root y squared plus d squared. And that will be evaluated at the upper bound, and we will subtract it being evaluated at the lower bound. So we're cruising along here. So now, let's get ready to do that. Get ready for this evaluation process. So first thing I'm going to do, there's a d squared here. He's not involved. He's a constant. I can actually pull him out front. So I have a d already up here on top. When I pull the d squared out from the bottom, it will cancel with the guy on top. So I will then have lambda times d over 4 pi epsilon naught d. So now kind of clears it up a little bit. So now I can evaluate this at the upper bound and the lower bound. So evaluated at the upper bound, I will have L over 2 over L over 2 squared plus d squared to the 1/2 minus this evaluated at the lower bound. Negative L over 2 over negative L over 2 squared plus d squared to the 1/2. So now, interesting thing happening here now. So d in the x equals. Okay, so actually, this d is gone. Remember that d is gone because there's 1 here and I pulled the d squared out. So he canceled with one of the 2 on the bottom. So there's no d there anymore. All right. Crisis averted. So one of the things to notice here, this guy right here, this negative L over 2, well, it's squared. So you could think of this as negative 1 times L over 2, and you can square the negative 1, and it would just be a positive 1. So believe it or not, these two fractions have a common denominator. So we can combine these two. So we would have lambda over 4 pi epsilon naught d times, all right, so these have a common denominator, as I explained why. The negative right here is squared. So what we have here is, let's just look at the top. We have L squared, which is 1/2 L, minus negative 1/2 L. Well, 2 negatives make a positive, so it's 1/2 L plus 1/2 L. Half of an L plus another half of an L is just an L. Okay, and then on the bottom, as I explained before, this is a common denominator, L over 2 squared plus d squared, and that is all raised to the 1/2. And we are almost done. We do not want lambdas in our answers, typically. So remember, lambda is actually Q over L. So if we throw Q over L in here, then we will have Q over L 4 pi epsilon naught d times L over 2 squared plus d squared to the 1/2. This L would cancel with that one. And we were left with the electric field in the X would equal, on top we have the charge on the wire, and on the bottom 4 pi epsilon naught d, the distance away, times the square root L over 2 squared plus d squared. And that is it. That's what we were trying to get to. Okay, a little bit tricky. This, I think, is the hardest one. You even have to know a relatively obscure integral in order to arrive at the answer. There are a couple little questions here, though, that we also, something else that once we have this answer, we need to kind of take a peek at. And the first question is, what if L, what if the length of the wire approached infinity? Well, if that's the case, let's look at what would happen. In which case, then the electric field in the x, well, this is the limit as L. We can go ahead, limits can be used all the time. If you want to know what happens when something goes to infinity, you can treat it like a limit problem. So then we have Q on the top, and then we have 4 pi epsilon naught d times the square root. Okay, this is what we just derived. L over 2 squared plus d squared. But, and we just did a problem like this in class where with that dipole, when something is way, way, way larger than something else and it's squared, you can disregard the other thing. So in this case, check this out. This guy is going to be infinitely large because L is going to infinity and he's being squared. This is just some constant squared. He is going to get dwarfed by L over 2 squared. So this guy becomes insignificant, so we can disregard him. Then this turns into the limit as L approaches infinity of Q over 4 pi epsilon naught d. So this would, now that d squared is gone, this is the square root of one term inside that is squared, so the radical cancels with that 2. So this is just L over 2. Okay, so then 4 divided by 2 here on the bottom, I have Q over 2 pi epsilon naught d times L. But don't forget, Q equals L times lambda. Actually, why am I doing, oh, that's one way to look at it, but don't forget what lambda is. How about we'll do it that way instead? Don't forget, lambda is the total charge over L. Well, that's what I have right here. Total charge over the total length. It's a good thing we have that because remember, just because L goes to infinity, that makes you want to go ahead and throw infinity in here and say the bottom of the fraction goes to infinity. But if it's infinitely long, then the charge is going to go to infinity. Okay, because for every length, there is a charge to it. So if it's infinitely large, there's an infinitely large charge. Okay, that's why we have this ratio right here. So in this case, we could throw the lambda back in. And the answer would be lambda over 2 pi epsilon naught d. So if you had this ratio of charge to length then, and you know how far away it was from this infinitely large wire, you could still answer the problem. One final question, last one. What if d went to infinity? Well, start with the same thing. Now it's the limit as d approaches infinity of Q over 4 pi epsilon naught d times the square root of L over 2 quantity squared plus d squared. Well, now this guy's infinitely large. His length, this is inconsequential. So now what I have is the charge over 4 pi epsilon naught times d squared, which is, in fact, this is, remember this is Coulomb's constant right here. So this is the charge times the distance away. So this acts, the wire itself will act like it's like a point charge. It won't act like a wire at all. And that makes sense because the length is nowhere involved here. And think about it for a second. If you have a wire that's this long, well, if you went infinitely far away from it, it would appear as a dot. Okay, it would not appear to have any length at all. Okay, so that is everything with that derivation. That's the big one. So I'm going to go ahead and get ready for the next one. So make sure that you know how to do this one. All right.